Dr. Srijani Mallik. Okay. So the next speaker we have is Dr. Srijani Mallik. So Dr. Srijani Mallik is at present postdoctoral fellow at CNRS France. She is there since April 2019. And in CNRS, she is working on studying spin-to-charge interconversion in 2D electron gases. She was awarded her PhD degree from NICER Bhubaneswar. And during her PhD, she worked on in the field of organic spintronics. In today's talk, Dr. Mallik will talk about spin-to-charge interconversion using 2D electron gas-based system. So on to you, Dr. Mallik.
Thank you. Can you hear me?
Yeah, we can see the screen.
See the screen and hear me also, right?
Yeah, we can hear you.
Okay. Thank you very much for the introduction, and also I would like to congratulate Professor Muduli for arranging such a beautiful conference, and also would like to thank him for giving me the opportunity to present my recent work on spin charge interconversion in oxide-based two-dimensional electron gas systems. So, in this talk, in this talk, first I will briefly discuss about the conventional oxide two-dimensional electron gas based on strontium titanate, and then I will discuss our approach to fabricate and also study the spin charge conversion in metal with strontium titanate based two-dimensional electron gases. Further, I will discuss more about spin and charge interconversion in a comparatively newer today family, which is which is the potassium tantalate based 2DEX. So to begin with, almost 20 years back, Otomo and Hwang, they discovered that if you deposit like few unit cell of lanthanum aluminate on top of strontium titanate, although both the lanthanum aluminate and the strontium titanate, they both are insulating perovskite materials, but they found that at the interface of these two insulating materials, the interface was conducting. So basically, by the charge reconstruction in the lanthanum aluminate at the interface of lanthanum aluminate and the strontium titanate, they discovered a two-dimensional electron gas, which was very nicely conducting up to quite low temperature. And later, it has been also proved that this electron gas is really 2D in nature. And these two-dimensional electron gas, they have a lot of very interesting properties. Like they have very high electron mobilities, then high spin orbit coupling, low temperature superconductivity, quantum Hall effect, and very nice gate tunability. So many more. So this oxide two-dimensional electron gas immediately became quite a hot topic since then. And then, but there were many reports where people observed such kind of two-dimensional electron gas, but with different insulating perovskite materials. But the problem with this is this involves really high temperature PLD growth, because like the perovskite materials has to be really in good quality. The interface has to be very clean and epitaxial in nature. So this involves quite high temperature growths and complex growth procedure, to be honest. Then like 5 years back, there was a report by Rodel et al. Telling that it's also possible to achieve similar two-dimensional electron gas by depositing just few angstrom of aluminium on top of strontium titanate by molecular beam epitaxy. So by using this idea, what we did is we grew a few angstrom of different metals, but using DC sputtering at room temperature on top of strontium titanate. So basically what happens is when you deposit metal on top of STO, the metals pull out oxygen from the STO surface and they become metal oxide, and in turn at the interface between the metal oxide and strontium titanate, oxygen vacancies are created, which gives rise to the two-dimensional electron gases. So we cannot use any metal, to be honest. So the criteria to achieve the reduced STO is that the work function of the metal has to be lower than that of STO, and the enthalpy for formation of metal oxide has to be also lower than that of STO. So in this case, we use tantalum, aluminium, yttrium, and gadolinium because all these materials fall under this criteria. And here I have shown how they are related with respect to the enthalpy for formation of metal oxide. So when we grew the sample, we immediately study the X-ray photoelectron spectroscopy. So here I am showing the data. So in the inset, this is just for the STO substrate, where we can see only one peak for the titanium 4+ state. This means the substrate is completely oxidized and no oxygen vacancies are present at this moment. Then we deposited 4 angstrom of aluminium, and immediately we can see the evolution of titanium 3+ peak, telling that oxygen vacancies are created. And as we increase the thickness of aluminium, we can see that the intensity of the titanium 3+ peak increases, as well as titanium 2+ peaks arises. This means like more and more oxygen vacancies are created in the substrate. And we observed similar things when we deposited tantalum, yttrium, and gadolinium. So for all the cases, we could achieve reduced STO, where we can see the peaks corresponding to titanium 3+ and 2+. But if we compare like how much we are reducing the STO depending on the material, then we obtain the highest reduction for gadolinium, more or less similar with yttrium, then a bit less for aluminium, and the least for tantalum. And this trend actually matching very well with the trend of the enthalpy for formation of metal oxide. So far we obtained like the highest reduction, let's say with gadolinium and yttrium, and then we did the magnetotransport property measurement in these samples. So for all the samples, we could see the formation of 2 because we see that all the samples are very nicely metallic down to 2 Kelvin. But here I would like to bring your attention that for aluminium, tantalum, and yttrium case, the ratio between the resistivity at room temperature and low temperature are more or less similar. However, in case of gadolinium, this ratio is much larger. And normally this ratio gives information about the mobility of the electrons. So from here we suspected that probably the mobility of the electron in this case will be much higher. We also calculated the carrier densities of these samples from the Hall measurements. And for aluminium, tantalum, and yttrium case, we could see quite a nice trend, like the carrier density increases with the thickness. However, for the gadolinium, no such trend were observed. Also, in case of the XPS analysis, we got that like yttrium and gadolinium, they were giving the highest reduction in STO, like more oxygen vacancies. However, the carrier density was obtained the highest for aluminium. So from here, we learned that a higher concentration of oxygen vacancies STO does not always lead to like the highest mobile carriers. This also depends on the reoxidation and diffusion coefficient of the native oxide. So here, because I already showed to you that for gadolinium, things are not really matching with the other 3 materials. So we wanted to know more what happens in this case. So we did the magnetoresistance measurement. And normally in case of oxide 2-dex, the magnetoresistance measurements are very parabolic in nature. However, in this case, we saw very large and completely linear MR, which is very unusual for the oxide 2-dex. And the MR value also normally are close to 50%, whereas in this case, we obtained like more or less 300% of MR. So, and the mobility, as we expected from the Alvarez ST, the mobility is really high, which is like 15,000 centimeters square per volt second, which is like 10 times larger than what normally we observe for other strontium titanate based 2-dex. So we really wanted to understand what is happening in this case. So for this, we did some structural analysis, the AFM measurement, as well as the cross-sectional TM measurement. And to our great surprise, we found that the growth of the sample is really strange, like because the oxygen formation enthalpy for gadolinium is the least in this case. So gadolinium really likes to pull out oxygen a lot, and it likes to be oxidized completely crazily by forming bubbles like this. Although we deposit like, let's say, only 5 to 6 nanometer of gadolinium, however, the radius of these bubbles became more than 30 nanometer. because from the yield analysis from TM, we actually saw that inside these strange bubbles, this is completely hollow. So here we have the gadolinium oxide, but this part is nothing. So what we understood that below the bubbles and beside the bubbles, the electron mobility gets strongly changed. And because of this, instead of having a normal usual MR, we started seeing this very large linear MR. So, but I will not discuss about this sample much because we also saw a lot of interesting properties in this sample. However, this will not match about with today's topic of discussion, because I'm going to talk about the spin to charge interconversion. And of course, in this kind of sample, I would never like to perform. So from now on, I discard the possibility of spin to charge conversion for the gadolinium steel sample, and we concentrated on the aluminium yttrium and tantalum based strontium titanate 2-deck samples. So to do the spin to charge conversion, because this is a two-dimensional electron gas, the main spin orbit coupling material is the Rashba spin orbit coupling. So thanks to the first speaker, Professor Prashanto Kumar Muduli, who really explained very well the Rashba mechanism as well as the charge to spin and spin to charge mechanism. So I will be really fast here. So we have already seen that because of the presence of the Rashba effect, there is a momentum dependent splitting of the energy bands. And if we see the cross section, we end up with such two concentric Fermi contours with opposite chirality, where the spin and momentums are always locked. And this Rashba spin orbit coupling enables the possibility to do the spin to charge as well as charge to spin conversion. So if we in such system, if we pass a charge current, then the spin contours will shift like this, and we will end up with some uncompensated spin density, which can also pass through the adjacent layer by giving rise a spin current through direct Edelstein effect. And the reciprocal effect is known as the inverse Edelstein effect, where let's say by spin pumping, if we inject a spin current in such system, then the contours will opposite direction, giving rise to a charge current. And as you have already seen in previous two talks, that the figure of merit of this spin to charge conversion is known as lambda, which is proportional with the Rashba coefficient as well as the spin momentum relaxation time. So equipped with this, we did the spin charge conversion study in all our samples. So of course, to do spin pumping, I need to do ferromagnetic resonance experiment, and I need a ferromagnet. So on top of the metal oxide, I deposited 20 nanometer of permalloy, which will act as the source of spin current. So when we perform the ferromagnetic measurement, then at ferromagnetic resonance, a spin current is injected in the two-dimensional electron gas, and due to inverse Edelstein effect, a charge current is generated perpendicular to this direction. And we also did gate dependent studies. So basically, if we deposit a back gate contact, and then with the gate voltage, we can tune a lot the carrier density of the samples, basically by moving the Fermi surface. So we studied the spin to charge conversion in all these samples, and we saw, because the 2-deck is the same because it's in STO, so the nature of spin to charge conversion obtained for different gate voltages are also similar. We always see similar to maximas. However, it's not exactly the same. We got the highest spin to charge conversion for aluminium in compared to tantalum and yttrium, and this is because it does not only depend on the alpha but also on the tau, because the alpha for all three cases are same, but the tau depends on two things: the tau of the 2-deck as well as the tau escape, which is the possibility for electrons to leak out from the 2-deck to the ferromagnetic layer through the metal oxide, which is acting as a tunnel barrier. Now, in case of aluminium oxide and tantalum oxide, this tau escape is in the range of nanosecond. However, for the yttrium oxide, it's in picosecond. So, which is also similar to the tau 2-deck. So, this way we can tell that, let's say for yttrium oxide, it's much easier for the electrons to leak out. So, it's not a good tunnel barrier. So, but however, for the aluminium oxide, this is the best, because this is really keeping the electrons in the two-dimensional electron gas, prohibiting it to leak out to the permalloy layer. So this is why we got the highest spin to charge conversion efficiency in case of aluminium, and depending on the gate voltage, the maximum we got is 25 nanometer, which is pretty large and like much larger than that time reported topological insulators or other interfaces like platinum, let's say. So from this study, we realized that, okay, aluminum strontium interface is really the best to give the high spin to charge conversion. And now we wanted to focus on a newer family of 2DEC, which is based on the potassium tantalate. So potassium tantalate is also an insulating perovskite and has many similar properties like strontium titanate, like they both are quantum paraelectric. And it's also possible to generate 2D electron gas in KTO by depositing other insulating perovskites similar to SO like lanthanum aluminate, lanthanum titanate, etc. However, why we think that KTO will be more interesting than SCO because the Rajva spin orbit coupling in KTO should be much larger than the STO2DEX because of the presence of this tantalum, which is titanium in case of strontium, and we know that tantalum is much like it's a heavy metal, it's higher than titanium. So this is why we expect that the Rajva spin orbit coupling will be much higher, which may give rise to higher spin to charge conversion. And some preliminary report actually tells that the Rajva coefficient in KTO is around 70 milli-electron volt angstrom, whereas till date for STO the highest was found close to 50 milli-electron volt. So we can already see that there was some progress, some hint telling us that KTO will be more promising than STO probably. So with this motivation, we started working on this and we did exactly the same. We grew aluminium on top of KTO at room temperature, and the aluminium got oxidized by taking oxygen from KTO and thus forming the 2D electron gas at the interface. So similarly, from the X-ray photoelectron spectroscopy, we can see that initially without any deposition, KTO had only tantalum 5+ states telling no oxygen vacancies. And then when we deposited some aluminium, we can see the evolution of peaks corresponding to tantalum 4+ and tantalum 2+ state, telling that the 2DEC has been formed. And then we did the magnetotransport measurement, which also shows us that very nice metallic behavior of the 2DEC. From the Hall measurement, we calculated the carrier density for these samples as well as the mobilities. And in this case, we saw that the mobilities are of similar order of magnitude in case of the in case of the aluminium strontium titanate samples. So aluminium STO samples and aluminium KTO samples, they both gave us similar order of magnitude for the mobility. Now, because I said this is a new system, so we don't know much about this. So we wanted to know more about the band structure of this system. So we performed the angle resolve photoelectron spectroscopy, that's RPES. So to do so, we grew 1 or 2 angstrom of aluminium by MB on KTO because this MB chamber was in situ connected with the RPES chamber. And then after growing the sample, when we immediately transferred into RPES chamber and measured the band structure, this is what we observed, where the band structure consists of a combination of few light bands which are with dxy orbital characteristics and few heavy bands which are with dxz characteristics. And also for the first time for any perovskite materials, it was possible to resolve the Rashba splitting using RPES. So here you can see like this part is the zoom of this full image where you can see like we can see the splitting of 2 bands. These are the Rashba splitted bands. And of course, to understand this, we needed some theory support. So we collaborated with the group of Ingrid Matik in Halle, who performed the tight binding fits for this RPES measurement. And from there, it has been calculated that the Rashba splitting for this orange band pair is 320 milli-electron volt angstrom, which is huge, 1 order higher than the STO2DEX. So of course, this is theoretical. So we wanted to measure in our sample this experimentally. And to do so, we took the advantage of direct Edelstein effect, that is the charge to spin conversion. So in the sample, if we inject a charge current, then due to the direct Edelstein effect, a spin density will be generated along the y direction, let's say. And if we now rotate our sample in plane with respect to the magnetic field, then the angular dependence of the resistivity will be dominated majorly by these two terms. The first term, which is known as the bilinear magnetoresistance, this varies as sine theta, and the second term, which is known as the quadratic magnetoresistance, this varies as the cos theta. And if we take the coefficient of these two magnetoresistance terms, then for BMR, this varies linearly with the current density as well as the magnetic field, and for the QMR term, this varies quadratically with the magnetic field. So we performed this measurement on our sample, and we can see that yes, the BMR terms really varies as the sine theta, and the QMR terms varies as cos theta. And when we calculated the coefficient of BMR and QMR, then as expected, the coefficient of BMR varies linearly with the current density as well as the magnetic field, and the coefficient of the QMR varies quadratically with respect to the magnetic field. Now here I would like to bring your attention that the coefficient of BMR carries information about the Rashba coefficient. So if we take the ratio between the BMR and QMR, then we can actually calculate the Rashba coefficient, and this is what we did, and we found the estimated Rashba coefficient is in between 70 to 280 milli-electron volt angstrom. So this is really in good agreement with the theoretical calculation by fitting the RPS measurement. So this is very nice. So this means in our sample we have really high Rashba coefficient. This means this will be very efficient for spin to charge conversion. So we performed the spin to charge conversion also in this sample. Similarly, we deposited permalloy and we did FMR measurements. And exactly at ferromagnetic resonance, we got very nice symmetry signal of spin to charge conversion, which also flips by changing the polarity of the magnetic field. However, when we calculate the lambda value, it came out close to 3 to 4 nanometer, which is similar order of magnitude of STO2DEX. However, we had like one order of magnitude larger alpha R, but the lambda did not improve. This is because the lambda also depends on the tau, and the tau depends on two things: the mobility of the sample, and like the mobility of the electrons in the sample, and the effective mass of the electrons. Now, the effective mass of the electrons are material property. So in case of STO2DEC, this is like close to 1 to 2 value. However, for the KTO2DEC, this is like 5 times less. So because as I already told you that the mobility of our aluminium STO and aluminium KTO2DEX both are similar. So even if we gained a lot with the alpha R, but we lost because of the effective mass. So to really utilize the gain in the alpha R, what we need to do in future is to increase the mobility of the samples. This can be achieved by changing the materials. This we have seen in case of the STO. So we have to do in future this kind of studies so that we can have really high mobility samples to take advantage of the very high Rashba coefficient to achieve very high spin to charge conversion. And with this, like I would give you another very brief information about the superconductivity, because it has been found for strontium titanate like long ago it's superconducting. However, for KTO there were many like for many years people were looking for superconductivity in KTO, but it was never possible until last year when a group from Argonne Laboratory in US, they found two-dimensional superconductivity in KTO2DEX, however, along 111 direction. So, and just after that, it was also discovered that KTO110 direction is also superconducting. So far what we know is KTO001 direction, there is no superconductivity. However, superconductivity has been found for 110 as well as 111 directions. And for both of these directions, the superconducting critical temperature is much larger, like one order of magnitude larger than STO. So in our samples also, we did the same. We took a KTO111 and we put aluminum oxide. And when we measured this, we also found the formation of 2DEC as well as the superconductivity close to 2 Kelvin. And we have also seen, we have also shown that by varying the the carrier density, basically varying the growth conditions. You can vary the carrier density, and like this you can tune the superconducting TC. And also we did gate dependent measurements, for which we show that if we are at very low carrier densities, this means applying very less negative gate voltage, there is no superconductivity. However, we can tune the superconducting TC with higher carrier density. So it is actually possible to switch on and off the superconducting TC with the gate voltage. We did also other measurements in this work to understand the nature of the superconductivity, but I will not go into the detail. So with this, I would like to summarize my work, telling that it was quite easy to fabricate 2 decks with STO and KTO with using a simple technique as sputtering, and we achieved very high spin to charge conversion with aluminium STO2 decks. And also first time we observed using RPS the Rajba splitted bands. And also we believe, like we saw that the KTO2 decks have higher Rajba spin orbit coupling than STO, although we could not still achieve very high spin to charge conversion. But we believe that in future it will be possible to achieve really high spin to charge conversion using such systems. And also we have the superconductivity. So as future perspective, as I said, that we need to grow higher mobility samples. I did not mention, but I have been working with Intel company in realizing some beyond CMOS future spintronic devices where I need to find the most efficient spin to charge converters. So for this, these KTO based 2 decks are really promising, and also the discovery of superconductivity now adds another degree of freedom to this. With this, I would like to thank all my team members and the collaborators who significantly helped me in all the works, and thanks to all of you for your kind attention.
So thanks a lot, Dr. Jenny, for the very nice talk and the amazing results. So now the audience can ask questions.
Hello, Srijani. Very good talk.
Thank you, sir.
So I had one question actually regarding this inverse Rajba-Einstein effect. How do you determine normally the sign of the effect, whether it is positive or negative? How do you normally do it in the lab? Because this lambda can be both positive and negative, right?
Yes, the lambda can be both positive and negative, actually depending on the sign of the Rajba coefficient. Because depending on, okay, maybe I will go to the band structure, because I did not show the band structure of STO here. But let's consider the band structure of KTO, which is more or less similar to STO. So depending on which bands you are probing, the Rajba coefficient can be the Rajba coefficient can change the sign. So depending on the sign of the Rajba coefficient, the spin to charge conversion sign also varies. And normally what we see, like if let's say your alpha is negative, then with the positive field in, let's say in this case, like for the positive field, you will still see negative spin to charge conversion if let's say your alpha is negative. But if your alpha is positive, then with the positive field you will see
that is fine.
positive.
I'm asking you general experimental point of view. You need some reference. Positive is negative is basically depends on which lab you are. So do you use some kind of reference that this is positive, and then accordingly you know?
No, but when we measure with respect to the magnetic field, we can clearly see from the signal how it is coming, like which side of the conversion. And also, like we always do theoretical studies from where we can determine the sign. And as I showed, like from charge to spin, we can do we can measure the alpha. From here also we can do gate dependent studies, and from gate dependent measurements we can tell where the alpha will be positive and negative.
Okay.
Is there any other question from the audience? So Dr. Srijani, I have a question. So your aluminium STO interface, you told it shows a very high charge to spin conversion. So
Yes.
have you tried using it for some kind of magnetic switching?
Magnetic switching?
Like
But
using that spin current to switch a magnet, like a perpendicular magnet or an in plane.
No, I have never tried this, but in principle, in the structure, like if you just consider the aluminum and SCO, then there is nothing magnetic. But you are
No,
telling
but
that
if you put a layer
using
of
this,
magnet on
yeah,
top of aluminum, can the
yes,
spin current that is generated, can it switch the magnet?
probably not.
Okay. Okay. So Vincent Cross, I think he has a question. So you can ask.
Yeah. Hello, Srijani. Maybe I could ask a question in the lab, but let's use this opportunity. When you estimate the Rashba coefficient from the BMR and
Yes.
QMR, why do you have
Yes.
such a large uncertainty, I would say? Because
Yes.
the BMR and QMR curve looks with very, why do you,
No,
why the
yes,
estimation is
I
not
will
better
tell
than
you.
that? You just make the
Yes.
ratio.
Basically what we do is we always take the ratio between these two, and when we take the ratio, the tau square they get cancelled out, so we do not need this. The field information we know. What we do not know here is the G factor, and the G factor, it's quite hard to estimate, and for the potassium tantalate it's not very known. In principle we did similar thing for like similar measurements for STO, and there the estimation of alpha is much better because the G factor is really known and we could do it. However, for KTO, like it's not really known, and we had to really guess, like we had to do some very good guesses. So this is why, like if we take similar values like STO, then it comes out close to 70 millielectron volt angstrom. However, if we try to consider that for KTO, what are the other factors that can play into the role, then it comes out close to 280. But because we really do not know the exact value of the G, this is why we have this uncertainty. But probably with future measurements and maybe some other reports, we can make it better.
Okay, thank you.
Okay, if there is no other questions, so I would like to thank you, Dr. Srijani, once again for a talk.
Thank you.